Thank you all for coming out today. We're pretty excited to share our tool with you. I want to do a quick crowd poll before we start. By show of hands, how many people has ever discovered a problem in production? Right? And that's pretty much all of us, right? Yeah, we're all here at Observability Conference. Now, who has discovered a problem in production that was hard to figure out? Like, that happens more times than it should, right? Now, who's had a problem in production that you couldn't reproduce outside of production? And those are the worst, because those are really hard to figure out. When you can't reproduce it, how do you verify that's the actual source, right? So those are some of the things that led us down our path. And we heard earlier about the live debugger, which is pretty interesting. It's pretty cool. We've had our tool for a little while now already, and I think we'd give a little more context than what Datadog has, even though theirs is a little more out of the box. So a little intro to our team. Our team maintains an orchestration layer, and our orchestration layer has about 150 microservices behind one GraphQL schema. And we sit between a lot of front-end applications and many, many back-office systems. But what our orchestration layer does is provide APIs for customers to manage their accounts, whether that's stopping services, managing service-specific features like devices on your home network. That all happens through our API and all the systems that we connect to. So we are ultimately a middle layer, and we isolate all the changes from all the back office systems and all those front-end applications. But in order to do that, it's a little complicated. So connecting to that many different back office systems, there's 70 different internal separate systems that we talk to in order to enable customers to manage their accounts. We also have 10 streams of data coming in from Kafka, and we talk to 7 external vendors as well, and we bring all those integrations together. However, we have a baseline level of entropy of constant change. All those systems that we connect to, they're always in flux. They're evolving APIs, adopting new tools, technology, modernizing. So there's a constant level of change that we're working with. And despite all of our processes and validation and communication that we have, sometimes we still miss on catching everything. And that's because we're all human. For a little perspective, our orchestration layer team is about 80 developers in 8 teams. But when we talk to 70 different back office systems, there's hundreds of people involved there. There's a lot happening, and so there's space for human error. Now, another thing that makes bringing all that data together difficult is that there's a amount of variability across all of our customer accounts. So Charter serves customers in 40 different states. And across all those different states, we have different markets. There's different plans and things that are available to different people in different places. Customers can bring their own equipment, so they can bring their own modem. They can bring their own cell phone if they have the mobile service. And so there's a lot of different variability, a lot of different things that are available across everywhere Charter provides service. And because of that, sometimes our issues only affect a subset of customers. There's something about their account that either the devices they have, the features, their plans, that causes a subset of them to have an issue. And we want to be able to identify that faster and resolve it for them so we can provide a better service, better product to all of our customers. And finally, we've done a lot of work on test accounts to better represent what we see in production, but that's only a small slice of the total combinations of things that exist within our production. So bringing all those systems together is kind of complicated. So here we have a single client request. There are 12 microservices within our orchestration layer that were part of this client request. And this is only showing our orchestration layer. Those 12 microservices made 16 different requests to 6 different back office systems, all to fulfill a single front-end request. So you can see how much is going here. You can notice the layers and dependencies from left to right of all the different services and how they interact in order to fulfill that one front-end request. Now, where it becomes difficult is that service highlighted in green, if it happens to throw an error, it's hard to understand where the error actually originated. Was there bad logic in that service that caused that error? Did one of these other services that it made requests to, did they have some bad business logic, return something unexpected? All of these are all getting data from back office systems. So did one of those back office systems return something unexpected, or did they change their API or do something? So we have even more services in the middle to add to the layers of nesting. And when you also consider our persistent data store and our cache, there's a lot of different places where something could have gone wrong for our service in green to cause an error. So it's really tough to understand where that problem actually originates. Now, if you recognize that last view or this view, we definitely take advantage of Datadog, and Datadog definitely helps a lot. But here's that same transaction in a flame graph from APM. You can see all the nesting of layers from top to bottom of all the spans that are involved there. And this only includes our orchestration layer. So this is not including any of the back office systems as well. And so Datadog gives us more context. We could see here that where our error occurred, we were making a request to our blue service. And so Datadog definitely helps us. With that context, we can see what part it was actually doing, the request that it made, the API, status code, those sorts of things. But it's still hard to understand if the problem actually originated from our service that threw the error, or our blue service, when it interpreted the data it got from back office, or did our back office system return something else, or did our blue service break its API contract and not return what we were expecting. So in order to quickly solve problems, we need a little more information to be able to understand where that problem actually originates. So we've tried a bunch of different things as developers to do this, but that usually devolves to more logs. And with more logs, you get more problems. A big one is log volume. So you got to consider the size of the thing that you're logging, right? And also how many requests your service gets. If you can't add a bunch of log statements to your busiest service in your cluster, an unexpected impact to the volume of logs you're generating. And with log volume, no matter what tool you use for logging, there's performance considerations and costs, direct cost considerations, right, of adding more logs. And also, we do our major releases about every 2 weeks. And we do patch releases on off weeks sometimes as necessary. What that means is that if you want to add more logs to your application and to get better understanding of what a problem is, you have to wait 1 to 2 weeks before you can actually get that. That's a pretty long turnaround time in order to solve a problem. Now, the other option is that if it's a gating issue, then we have to maybe roll back that service, roll back all the dependent services that are dependent upon new features within that, or we need to do an emergency deployment. And typically, both of those are usually heavy lifts, require a lot of people to be involved, and sort of all hands on decks. So we started asking some questions. We said, what if we could capture all these requests between our services? That would definitely help us to understand that if our service C here threw an error, seeing what the back office system returned would help us give us a lot more insight to where that problem actually happened. We could see, what data we got that caused us to throw an error. Likewise, if a service in the middle of the chain were to throw an error, having the context of what it got back from another microservice and what that microservice got back from the back office system can help us figure out where in that lineage of that data traversing that something went wrong that caused us to ultimately throw an error. So then we thought, well, if we had this data, why can't we just send that request from service B to service C again, right? If we have the headers, the request body, we can make it sort of reproduce. However, service C depends on external systems, right? So we need to find a way to inject a response or mock that response so service C can still do its same behavior, still reach out someplace, get its information, and do the same thing. Now let's say if we can make service C do the same thing again, what if we could attach a debugger to it, right? As you saw with the sort of live debugging, the value of being able to step through a problem from production and sort of see everything that went in to have that context of where the source of the problem is. So that notion made our developers really excited. Oops, back one. However, all this information is all raw traffic, right? So if we're gonna collect this information, we gotta collect, transmit it, and store it securely. We need to meet requirements for consumer protection and data retention. We need auditing and access controls. So if we're gonna collect this information, we gotta do it right. So that's something that we had to solve in the beginning. But when we decided that we we're gonna do this, we asked, well, why not? Why can't we do this? So introducing our tool, we call it catch and release, and we have our core functionality, which is reproducing that production behavior in isolation. So that means that we were able to capture all the HTTP request response data as it traverses across all of our microservices, and also capture all the Redis operations that we're doing as well, so we know what the cache look like. This is important because when we replay a transaction, we need the cache to look the same to make the service do the same thing. And we also are able to inject the responses. So services can make requests to other services or try to back office systems. And we can inject those responses so the service can still do its same thing and not realize it's not actually talking to anything else. This gives us the ability to do troubleshooting, regression testing with tens of thousands of requests from production to validate changes, and also do performance testing. And for some of what that looks like, I'm going to hand it over to Jeremy, who's going to show you a walkthrough of our tool.
Yeah, thanks, Robbie. Yeah, so I'm going to take you through the developer experience using this tool through some slides. My team got to be beta testers through the development process, so I'm pretty excited to share this with you. I'm going to highlight a few of the use cases. A little bit later, Robbie's going to talk about how all this data is captured, but I want to talk a little bit about the scale here. We're capturing something like 8 terabytes a day of data, and for a developer, using this tool, having that kind of information at your fingertips is amazing. The value cannot be overstated. So first up, we'll talk about general data inspection. In this part of the tool, we can observe that data using some search fields. You can see that we have transaction ID, trace ID, time frame, services, errors, operation names. For our example here, we're going to use connection state, this operation name, GraphQL operation name. This is used by our customers in the portal to determine if their modem, pod, router, that sort of thing is up and healthy. Our search results return a list of transactions that meet our criteria, as well as some metadata about that capture. So in our example, we'll select this first one. And here we get a bit more data about the transaction. We can see we captured 7 HTTP spans, 23 Redis spans. We also get our first view of services involved there. We have graph services, we have our domain services, and some upstream services as well. We also have some convenience links, so we can replay the capture. We'll talk about that a little bit later. We have a link to a Datadog flame graph, and then we can go look at some logs. We can expand this first Reddit span section to get an idea of what the structure looks like. So generally speaking, this is going to help us understand when, where, and what direction these things are going, as well as being able to see the specific requests and response. The other type of data here is HTTP data. In both of these cases, we can't really show you, obviously, the production data, for these use cases. But you can imagine, what that looks like. This is all that chatter, the requests, the responses needed to string together a successful call. This part of the tool is really great for understanding something about the existing data flow. As a developer, getting in there to understand how these calls resolve, the nuance of those things, down to the data. It's a bit open-ended at this stage, this use case, but that's generally speaking what we're using it for. And again, something like 8 terabytes of data a day is so cool when you're writing code. So Robbie's going to talk a little bit more about the architecture involved in capturing and replaying this data.
Mm-hmm. Thank you, Jeremy. So here we have a high-level view of the architecture of our system. On our left, we have our production Kubernetes cluster. Now this is handling our customer traffic. And as a request comes into our cluster, it traverses through our microservices. We get some data from back office systems and responses sent back. Now, another thing that's important over here is using Istio. We use Istio as our service mesh. And what that gives us is it's based on Envoy, and Envoy includes a tap filter, which gives us access to those requests that happen as they traverse through the system. And we built an aggregation pipeline that allows us to take all those individual requests and put them back into a single transaction. So once we have that transaction, now on the right side, we have another Kubernetes environment. And in this environment, this is where we allow developers to replay transactions and testings. Here we have Istio again, except here Istio sets so no outbound connectivity is allowed. And so notice there's no egress, and that gives us some isolation from interacting with production systems with either request volume or manipulating data in them for customer accounts. So when a developer wants to replay requests, they interact with our replay service, which hosts the UI and the APIs that Jeremy was just showing. And that service can then take that request that went into service A and run that request again, send the same headers, request body. And service A is going to do the same thing, send requests to service B and C. And what we don't have here is egress. And so we'll talk about this a little more later. But in this instance, service B makes a request out, a response is returned, and service B still does the same thing and returns the result back. So for a little deeper on how we capture data, here we have our production Kubernetes pod. Within our pod, we have 3 containers. On the right, we have our application container. In the center, we have our sidecar container, which has our logic for gathering this data. And on the left, we have our Envoy container. Notice all the traffic goes in and out through Envoy, because our Envoy is part of our service mesh, and it's controlling all the connectivity and data going in and out of our pods. So as a request comes into our application, Envoy is and Istio are managing our SSL across the whole cluster. So SSL is terminated there, and the request gets sent along to our application container. Now, our application container starts doing some work. It decides it needs information from another system, so it makes a request out. And this is in plain text because Envoy is, again, managing all that TLS. Now, once that request goes out and comes back and completes, our tap filter then it sends that request response data to our sidecar. So now that we actually can see the request that was made and the response that came back. So our application keeps working. It decides it needs to do some work within Redis and the cache. So again, this connectivity goes through Envoy again. But once that Redis operation completes, we have that instrumented so we see what the read or write was, and what the result of that was. So then our application finishes working, sends a response back, and as that response traverses through Envoy on the way out, again, the tap filter gives us that request response data again into our sidecar container, which then we can aggregate, we send the kinesis to rebuild the transaction as it traverses across our whole cluster. So now we're going to pivot back to Jeremy so you can see a little more of the tool.
Yeah, thanks, Robbie. So the next use case we're going to do here is what we call batch replay. Batch replay is a great way to regression test a service that has some changes. It's perfect to tell us what we don't necessarily know what we're looking for. It's useful to tell us what's making that burning smell. Some context on what we're doing here with this demo. Again, we're using the same operation name, connection state, and we're demoing something that if it was changed for customers, it's not really easy to find in API unit integration tests. This is like a nuanced change. We pushed a config change to our replay environment. Our change is a modification of signal levels used to determine the health of a modem. And we can check this change against our production data to see if there's anything that needs investigation. So when we run 10,000 transactions related to this connection state call, we can see that we have some modified fields. The summary here gives us a 40,000-foot view of what happened, but we can drill a bit deeper. In our results by endpoint summary, we can see there's some changes here related to connection state. We have 4% of our replays here that had changes, and in those change responses, we know that 7 of the fields were modified. So we can click this first one to get more detailed information. When we click into our results, we see a view indicating whether there was a removal, addition, or modification, indicated there by the plus, tilde, and minus. The connection state field here in the body is the most compelling for our demo, but you can see that we also see the remainder of any other changes there. When we look into that field in the body, we get another view that tells us that it's switched and there's a new value. So the new value is connected healthy. It also tells us that the type of the change was a replacement. That's enough to convince a developer to dig in on something like this. But we can replay this transaction and go a bit deeper. Before we do that, though, I wanted Robbie to talk about how these captured responses are injected.
Thanks again. So here we have a high-level picture of how we inject our responses. So we're going to step through this. It seems like there's a lot going on, but I think at the end it all makes sense. So when a developer wants to replay a particular transaction, they use that replay service and they start the process. The first thing that service does is stage some data in Redis. Now we have 2 things you can see that we put here. We have a key named rKey. That's a request key representing a response we want to inject, and also a key named foo with a value of bat. So once we have that data staged in Redis, our application sends a request to the service that it was destined to. So our application container for that service receives the request and starts doing some processing. The first thing it does is look up some data in Redis. So the application is going to do the same behavior, look up the key foo, and get back the same value that it saw whenever that transaction originally happened. So this, putting that data back into Redis, allowed our application to sort of see the same thing within Redis and do the same behavior, which in this case is decide that it doesn't like that value and reach out to another service to get more information. So when it makes its outbound HTTP request, again, it traverses through Envoy, and here we have our Lua plugin. What our Lua plugin does is take that request and first send it to our sidecar application, which then takes the information of that request, builds a request key, and look it up in Redis. It sees that there's a response to inject, so it takes that response, sends it back to our Lua plugin, which then writes back the original headers, response headers, and response body back to our application container. So at this point, our application container made a request out, and that it got a response back without that request ever leaving the application container itself. So our application container finishes processing, sends this response back, and our replay service then diffs the new response to the old response and sends it back to the developer. Now, sometimes we don't have a response to inject. And this is important when we are testing multiple microservices as all part of the same transaction. Now let's rewind a little bit. Now let's say, in this instance, our sidecar container is looking up request key 2. And there's nothing in Redis for that, so it doesn't find anything. Our sidecar container, in this instance, returns a 404 not found, which tells our Lua plugin to allow that request through to wherever it's destined. So that goes to typically another microservice, and the request comes back through Envoy, back to our application, and it completes this processing just like before. And so this happens at the service level, and so whether you replay a single transaction or a single request, or if you play tens of thousands of requests, the same process is happening. But for look, what a developer sees whenever you play a single request, I'll hand it back to Jeremy so he can show you that.
Yeah, thanks, Robbie. So here we are at our replay. We're going to execute this one and see that injection work. We can click to replay the original capture here. And this is sort of what I would think of as the third use case, or a third use case of this tool. Triage. You can use it for more than that, but I think it's really compelling for that use case. Here the tool populates the trace ID as well as the service that we want to target, and we can replay that specific transaction. When we see the results for this one transaction, we get all the HTTP call associated. The GraphQL operation name here results in 2 REST calls to our equipment domain service. The first shows no noteworthy diffs, but the second shows 2. And we can expand to see the response diff here. This gives us a clear view of where to spend our energy, but it also tells us these other fields that have changed. So we see that the connection state has changed from connected unhealthy to connected healthy, and an error field has been removed. We also, though, see the timestamp differences and whatever other related differences happened in that REST call. And I think this view highlights something that Robbie and the team did really well with this tool, which is at different points in the tool, you can see data in different ways. And with the amount of nuanced data that we have coming through, it's often good to be able to get those different approaches to find the thing that maybe you're not looking for, find the thing you are looking for, those sorts of things. But to understand this issue better, we're going to attach a debugger in our replay environment and replay the same transaction. So here we go to patch our services. In our replay environment, we have our services here. This page helps us to patch those services easily. Any user can see what services are patched for debugging, by who, when, as well as data about unpatched services. So for all the services, we can see the versions that are deployed in the environment, the commit related to that deployment, and a convenient button to patch the service itself. So if we patch that service to allow a debugger, in the background what we've done is we've reduced our replicas to 1, and we've patched the service to allow the debug port. We can see its status here as it gets patched. When it's up again and ready, we can see who patched it, when, all those sorts of things. We also get a convenience link here for shell commands. The convenience pop-up gives us the kube control, port forward commands, as well as a handy way to tail the logs. From here, it's pretty straightforward to start the debugger in your IDE of choice and debug in context. I think everybody's familiar with debugging in general in an IDE, but this is a bit unique. We're attached to a pod in our replay environment, from a developer's local IDE, and then replaying that transaction in question. For me, this feels like being able to write code, ship it to prod, see what happens, and then roll back the clock as if nothing happened. And this mock regression example here shows one of the things this tool is really great for. If we look back at this view, we see that in this example, our change caused a difference in 4% of the sample 10,000 calls. As software developers, we often have requests to fix something for somebody somewhere, but it can be hard to know if that's going to cause unintended friction for someone else. In this case, our example would have expanded what a healthy connection state would have been for modems. This would have led to customers feeling frustrated going to the portal, and then the portal would have indicated that everything was fine. So it's a nuanced change that we can avoid with a tool like this. And then, that's a mock example, but this is something that we actually did do in prod. This looks a little bit more dramatic maybe than it was, but the data doesn't lie. That's a big old change. It caused some friction for our customers. It wasn't the end of the world, but certainly something that we could fix. But the cool thing about here was the cycle of how this worked with this process. One of our front-end tech leads came to one of our back-end tech leads and talked about some friction they were seeing in the portal. Our back-end tech lead was able to suggest a change, put out a feature branch, put that in our replay environment, and put 10,000 transactions against it. It wasn't perfect. They were able to iterate on that, get that branch out again, replay those transactions. And then once we were happy with that, we were able to take that same replay against that new backend code, sanitize those responses, get that to our front-end team. They were able to mock that, make sure that we're happy with the UI treatment, that it does what we want, it doesn't have any unintended consequences. And then we were able to push this out. That whole process took about 2 days, which, historically that would have taken maybe a few cycles to do safely. And when that change went out, I slept like a baby. I was not sleeping. I was on call watching this. But it does highlight, I think we all end up looking at graphs like this during deployments. And a lot of times we're sort of looking for the opposite. We're going, oh, what's going to happen if this thing goes sideways? We just hope that nothing happens. But this was really cool because I was like, I'm going to watch this be successful. And so that was really exciting for me. In short, when we have the nuance of large-scale prod data at our fingertips, we can take bigger swings with higher confidence. This tool provides us a huge opportunity in experimentation. It's almost like having a canary release with zero risk, impact customers' dependent systems. And it gets to the core of what I like so much about this tool, which is developers can use this to refine their code, but at the same time, they're able to refine their skills. A tool like this gives them more insight and faster feedback so that they can improve their craft. And I think that's what really matters, and that's what's going to lead to the best product possible.
So, in summary, we talked to you about how our orchestration layer sits between a bunch of front-end applications and many, many different back-office systems. And pulling all that data together makes some really complex business logic. And when you have this much complexity, it's really hard to understand where the source of a problem is. But we showed you how we're able to build a system to collect some information and ultimately reproduce that errant behavior in isolation, which gives our developers a much better experience and also allows them to triage things and solve things more quickly. So we want to encourage you to think outside of the box and don't settle for the status quo. For us, that was logging, lots of logs, and trying to find a needle in a haystack sort of a thing, right? We asked a lot of questions. What if we could get this data? And what if we could reproduce that production behavior someplace else so we can actually work with it? What if we can attach a debugger? And we ask questions like, well, why not? Why can't we do this, right? Took a lot of conversations to get everyone on board, especially with security and other stuff like that, and make sure that we were checking all the boxes, but we were able to do so. So we also want to encourage you to innovate. We solved a lot of interesting problems over the course of creating this tool. And ultimately, a better developer experience leads to better products created. And that's the core of every business that's powered by software. So before any questions, I want to call thanks to our dev and testers who helped us build this tool. I want to call it the quote in the middle because it's my favorite. Someone said, "It has become so useful that we get blocked if it doesn't work, LOL." And with that, I'll open the floor for any questions.
Okay, we have 2 mics in the aisles for folks to line up for questions. But before that, let's give a hand to our speakers.
Thank you.
Hey, really good talk, really good tool. I'm very impressed by it. What are the next step for the tool, right? Like this is just for your company. Are you planning to create a sub part of it to give it to the community and things like that?
Yeah, so we haven't thought too much far and out in terms of open sourcing it. I think it's something, I think it's really cool. I think there are parts of it we could open source out.
Yeah.
Things like our aggregation pipeline are built on an internal framework. I don't think that team is ready to open source their framework, but I think there's definitely things that we could share. But I think it's something we could sort of take back to our leadership team and make sure they're cool with us putting that out there. Yeah.
Cool. Thank you.
Couple questions just out of curiosity. Really cool tool, by the way. So first one is what was the time frame from going from you had this idea to you have this tool that's in the hands of the developers for their debugging?
Yeah, so I think we're about 2.5 years into our journey. And the first year we had like a short contract, 6 months, do some POCs to get some help on board, see if can we actually figure it out? Can we work through the sort of tough problems? And we were able to do all that. So then the next 6 months we worked on, okay, well, how do we get it production ready? And so it took about a year to instrument the first few services. At that point, I think we only had about 3 or 4, but I think by about the end of the year or so, we actually had them in production, reporting this information. And that sort of got us our first use case of just doing the troubleshooting. And then from there, we built on top, and we had replay working for a single request, but we built on top be able to replay mini requests and do it in large batches. That sort of followed on the second year, and as we continue to route to more services. So I think we've had almost all of our services instrumented for since like the last fall or so. So that's probably 18 months-ish.
Okay, cool. And then second question, again, out of curiosity, what is like the maintenance cost or the maintenance burden look like for this? Because it seems like, correct me if I'm wrong, but it seems like you have to almost have a whole nother production environment set up that you can do the replays in?
Yes.
So what's that look like?
Yeah, so we run both the aggregation pipeline and which is a real-time app, right? And that second Kubernetes environment. Now that second Kubernetes environment isn't scaled to production, right? So we only have 1 or 2 replicas of each of the services to try to minimize on costs there. But I think our AWS spend is like the 15-ish K a month, and that's the aggregation pipeline and the replay environments. So that's
and you feel like the trade-off there of having simplified debugging for your developers is really paid back?
Yes.
Cool. Awesome.
Yeah.
Thank you.
Hi. I'm curious about how you avoid an over dependence on only debugging in production rather than like a staging environment. Do you have any like guardrails around that?
Yeah, so we do have a staging environment, and we have a lot of our partner teams, right, that all work with those front-end apps. They all do testing there as well. But because of the variety of what we see in production, it's hard to cover everything there. And so something we've been working on more recently is integrating this tool into our software development lifecycle process. So every release that we have, every 2 weeks, we are asking getting our dev teams on board to come and do regression testing on all their services, so that before people discover issues in, say, our stage environment, we've already found, resolved them, and have a good understanding. And that helps us to find issues that are sort of smaller as well. Does that answer your question?
Yeah. Thank you.
Yeah, I would add that our goal is to be able to move faster and deploy more often. But in order to do that, we have to reduce risk, right? And this helps us reduce that risk.
Hello. I wanted to ask if something wasn't caught in Redis, for example, and the request was like not recorded. How do you have what guardrails did you have in place to make sure like no changes were actually made when someone made a replay request?
Yeah, so our replay environment is entirely separate from the environment that's actually serving production, right? So it has its own Redis instance that's over there entirely. And likewise, all the other services, it can actually connect to any of our back office systems. Does that answer your question? I think I'm close, but not quite.
I know, but what if like the other, I guess, do your other microservices, do they make calls like to outside of your own services, or are they all like self-contained?
I mean, a lot of them, almost all of them connect to back office systems in some way, shape, or form, right? And so that's where it's important for us to isolate them so they can actually talk to those back office systems. But there's also the need for be able to inject those responses so they can actually do the same behavior.
Okay, thank you.
During the replay, how do you guys handle the PII data?
So the raw traffic, like the raw responses, are still shown to developers when they look at that data. So that's why we have the access controls and auditing. As soon as we get that data, it's encrypted outside of like the sort of all the standard encryption, right? So it's encrypted at rest, but we also have a field level encryption that we do as well across the data, so that we try to keep it as secure as possible through the whole process.
And you guys do that in the Lua filter, like in the Envoy, or
What's that?
do you guys do that in the Lua filter in the Envoy, or?
No. So when we collect the data is when we first do that level of encryption as well, right? In addition to like SSL and all the other sort of features you just turn on with AWS managed services.
Awesome. Yeah. Awesome tool. Yeah. Thank you.
Really great tool. You mentioned you're capturing like terabytes of data a day. How long do you find you have to store that for?
So we only keep it for 30 days, so we can stay under like CCPA and other sorts of requirements. The less we retain, the better. But we're trying to find that sort of, a lot of times, like our dev teams someone comes on like, hey, this user had a problem a week ago, and they weren't able to do something. Why, right? And so, probably 1 to 2 weeks is probably the minimum of what we need. But having, since we do major releases every 2 weeks, when we regression tests, like large services, we compare, we always use the latest production data. So we're comparing, this version of the service to the previous one that was deployed. And so that's something that we need about 2 weeks, but.
Awesome.
Yeah.
How you doing? Are you using anything like infrastructure as code to spin up the environment and make sure you're pulling in all the needed new containers?
Yes. So everything is all automated. So the environment, our replay environment, is all infrastructure as code. When we deploy our releases there, that's the same automation that deploys it to production. We just deploy that release into our environment first before it gets deployed to production. And so we have everything covered by infrastructure as code. Yeah.
All right, we are out of time. Thank you so much. Another hand for our speakers.
Thank you.